Good morning, everyone. My name is Paul Ian Kabasag, and for this SE 227 case studies, we'll be talking about the New Zealand earthquake case studies. And why I'm very interested in this particular region is a lot of the building codes and standards have really been motivated by this seismic area that is mainly in Christchurch and in Dartfield. And those are the two earthquakes that we'll be studying today, the 2011 Christchurch as well as the 2010 Dartfield earthquakes that really became the impetus for these building code changes for mainly masonry and concrete structures. The question that we'll answer is, why was the 2011 Christchurch earthquake more severe than the 2010 Dartfield earthquake? Was it the seismicity? Was it the damage? Or was it the statistics that occurred? That's what we'll uncover today. So without further ado, let's begin. So first of all, let me give you an overview of these earthquakes. The first one here is the 2011 Christchurch earthquake. And mainly the location of this earthquake and the geographic features were it occurred on a weekday, Tuesday, February 22nd, 2011. At about 12:51 p.m. in the afternoon. And the magnitude of this earthquake was 6.3 a moment magnitude that struck this region, as you can see, the Christchurch in the Canterbury area within New Zealand. So for seismology, the main features for these are that it was indeed a 6.3 moment magnitude, as I mentioned. But the intensity of it was very severe in the Mercalli scale, about 9, which is the shaking can be categorized as violent. So most of the shaking here caused damage considerable in special design structures. Mainly that we're going to talk about are the unreinforced masonry as well as concrete systems. And the depth of this was quite shallow, about 5 kilometers only, which will play a part into why this earthquake was more severe. And the peak ground acceleration was quite high as well, about 1.51 Gs. And then the max duration of the earthquake was quite short, only about 10 seconds. So the earthquake originated from a rupture of 8 kilometer by 8 kilometer blind fault. And the earthquake itself, when I say blind, it's unknown, and it occurred in an area that didn't have an actual name, as you'll see in the 2010. This was not the case, which this was also an oblique truss type of fault, and as you can see here, it was running from east to northeast, and at a depth of about 2 kilometers range from Kashmir to Avon Heathcote estuary. And it dipped down southwards an angle at 65 degrees from the horizontal beneath the Port Hills. And what caused the effects of this was a fault slip as much as like 2.5 meter long subsurface fault rupture of about 14 kilometers. If you look on this figure over here, you can see quite a comparison of the two earthquakes I'm going to talk about, but now let's focus on the red star, which is where the Christchurch, I believe, is right here, and this red line is where the fault line is, and then the yellow dots is where the subsurface rupture occurred, about at a length of about 14 kilometers, so quite substantial. And the green here are the faults or shocks that occurred in the previous year, the 2010 Dartfield, which I'll momentarily talk about. But I just want to show you guys quite a geographic relation to better understand where this earthquake occurred. So now let's talk about the structural damage. So in New Zealand, a lot of their buildings are mainly masonry and concrete. There's not a lot of steel or timber buildings. And what really were damaged most were the URMs, or under-reinforced masonry systems. And a lot of it, cause subpar or caused because of the subpar retrofitting. There was a retrofitting policy that they've implemented in their building code, but a lot of a lot of the area in the Christchurch was previously relaxed and was not really thought about as a area where it had that it had to have a mandatory retrofitting. So most of the retrofitting at this time were voluntary, and that subpar retrofitting techniques that were implemented during that time prior to the earthquake really led to a lot of these URM buildings either collapsing or partially or damage. And then besides that, there's also a lot of ponding. Ponding is when you have two buildings and they end up hitting against each other. So this ponding against adjacent buildings, as you can see here, is an example of a masonry building that's partially collapsed on the right here, which is right next to this building, taller building, that where during the earthquake allowed the building to move left to right, and the shorter building caused the damage in the shorter building, which is the masonry, that allowed it to some of the masonry blocks to fall off. So besides ponding, there are also some bonding failures between anchor adhesives and the masonry, as well as low strength mortars that led to poor grouting. And so the URM buildings was mainly the proponent of a lot of the damaged systems during Christchurch earthquake. But not only that, but there's also concrete systems, very similar effects. There were a lot of collapsing walls, as well as punching shears at slabs due to the high concentrated loads, as well as detached diaphragms, roofs, and some floors that had poor diaphragm to wall connection that allowed the diaphragm to fall out of the wall, so to speak, and then also as well as like combined lateral and gravity failure or shear axle failures at the columns. Most of the columns probably did not have enough lateral confinement, only gravity so it didn't have enough capacity for the massive horizontal forces induced, and altogether this also led to beam column connection failures, and besides masonry and concrete systems, we had others as well, where we had detached stairs. The stair to building connection were quite poor, as well as out-of-plane movement at beam wall connections and diaphragm wall connections. And besides just having like singular systems, there were also dual systems, like such as a steel EBF frame, as well as a precast concrete wall panel. And these connections, due to the relative stiffness difference, cause failures at the joints. And so now for the loss statistics, I want you guys to look at this figure over here. This is really one that I found quite neat. The green, yellow, and red are what we call when you call structural assessments. There is color coded depending on whether the building is restrictive for occupancy and depending on how damaged the building is. So to briefly talk about that, a red tag structure is one that has severe damage to the degree that the structure is too dangerous to inhabit. And then the yellow tag structure would be moderately damaged to the degree that its habitability is limited, maybe during only a day or not for so long. And then green tag structure may mean the building is either undamaged, partially damaged, so slight damage. And these are just statistics for each material, the construction material in Christchurch. As you can see here, so the more red, the more damage is mainly for unreinforced masonry. So that's mainly the cause of most of the structure damage. And other statistics that I found were the economic losses were estimated to be about $14 billion, and the building losses were estimated to be more than 60,000. And I think this is a combined amount for recent earthquakes that occur in the area. It's not just for the Christchurch earthquake in 2011. And the casualty losses range to about 185 deaths to 750 injuries. As you can see, this is the earthquake that had deaths, and while the next one now, for later, the 2010 Dartfield earthquake didn't actually have any deaths but only injuries. So besides these four features, now let's talk about the non-structural damage for 2011 Christchurch. And the one I want to cover, primarily the facility that got, or the community that got really a lot of non-structural component features got damaged, was the Central Business District. And this is primarily in the main city metropolitan of Christchurch. Per se, it's the city area, or in the middle of the city, which really got the bulk of the effect. And just before we talk about that, the main non-structural component damage sources were from inertial effects, building deformation, building separation, and interaction. So all four occurred here. And let's just talk about each one now. So for the first one, inertial or shaking effects in Central Business District, CBD for short, were mainly from a sliding unanchored equipment. This can be seen here. So as you can see, this personnel is looking at this equipment that slid really right across the floor. It was and this was quite a heavy equipment. It was about 25,000 pounds. And for building deformation, this was caused due to large horizontal earthquake forces, and this led to damages such as to interconnected facade components. Numerous facades of more modern structures, often comprised of glass and lightweight metal panels, were damaged and fell into sidewalks, threatening exiting occupants as well as search and rescue teams that were trying to enter the building to either conduct firefighting or search and rescue. And not only that, there were also building separation effects due mainly to the deformity of the building during the earthquake, or pounding, as I mentioned, two buildings hitting against each other, causing damaging one or the other, and then movement across expansion or seismic joints. So what these cause, damage such as minor cracking of partitions around window openings. So not so much damage there, but mainly the one that had a lot of effects as well as costs were the interaction between these non-structural components, and this was mainly due to differential movement of components, damaged ceiling and piping, not so much partition, ceiling and piping. And so in office buildings and retail shops in CBD, there was typically damage to ceiling grids, ACT, suspended ceilings with light fixtures, as you can see here. And this is the typically most of the buildings there. As you enter the offices and retail shops, a lot of the components have fallen out, and due to the interaction are shaking. And not only that, there was also overturned shelving, broken sprinkler pipes, and broken furniture and contents or furnishings of the building. The very common one I saw in like the New Zealand earthquake, we'll compare them later on again, but a lot of the storage racks collapsed in warehouses, and which really led to a lot of all the goods to be disposed, and it was really quite an extensive effort on their part. So with that, let's talk about the 2010 Dartfield earthquake now. And so similar features. So the location of this and geographical features were, it was during a Saturday weekend, September 4th, 2010, at about 4:36 a.m. during dawn. And the magnitude of it was 7.1 moment magnitude earthquake that struck Dartfield area in Canterbury region in New Zealand. And this is just a picture. kind of depicts kind of a very similar region. But do note that the Christchurch is one of the more popular areas of New Zealand, whereas Dartfield is more of I wouldn't say rural, but it's near universities rather than like main office industrial buildings. So the seismicity of the 2010 Darfield earthquake, whereas it was a 7.1 magnitude, the Mercalli scale intensity was 10. So this was in fact higher. So the shaking category here for an intensity of 10 is about extreme. And for an extreme earthquake, this means that there's some well-built structures are definitely destroyed more than the 9 violent shaking, and mainly masonry and concrete structures destroyed with their foundations as well as the whole building may have collapsed. And then this earthquake, the depth of the earthquake was deeper at 10 kilometers. The peak ground acceleration was shorter, about 126 or G's, and the duration is longer, about 40 seconds. So just talk about how the earthquake originated. So this, in fact, had a known or non-blind fault. This is the Greendale fault, as you can see from here, and it was a strike-slip fault versus a truss fault, and running east-west within the crust of the Pacific Plate near the eastern foothills of the Southern Alps, at the western edge of Canterbury Plains, causing a surface rupture nearly 30 kilometers and fault scarps that locally exceeded 4 meters of right lateral, about 1 meter of vertical dislocation of a ground surface. So just to look at this figure a little bit, so this actually shows a heat map of the Mercalli scale, intensity scale. So the more red, the worse it is, so extreme. And then the lighter the color is, the less intense the shaking. So as you can see, most of the intensity was concentrated near, obviously, where the Darfield is, and somewhat near Christchurch, but not so much. Okay, so now for structural damage. Again, most of the systems that were damaged in this 2010 Darfield earthquake were URMs, concrete systems, and other systems. So for URMs, the damage was in-plane shear cracking of walls. A lot of it was propagated by the infill walls. These buildings actually had masonry infill non-structural walls that didn't have any reinforcement, and due to that, they cracked along across the wall. And so there were, similar damages occurred, such as low strength mortars that led to poor grouting. So when you have poor grouting, usually there's not enough. There's a lot of voids between the cells, allowing more dislocations and damage of the masonry walls or masonry infills. So the gable walls also were detached due to poor connections. This caused falling masonry, and you can see that in these two pictures here. So as you can see, the higher you are, upper story, the more or larger forces that you're gonna be induced to the structure, seismic forces. So as you can see, the upper floors here had masonry. The gable walls were damaged and had falling masonry, as well as this one. The gable walls here were damaged and fell through the streets. So, and then common to both of them, the 2011 as well as 2010 earthquakes, were the subpar retrofitting of these areas, and due to the lack or lax retrofitting methods and policies that was implemented in the region. And for concrete systems, the damage evidence shown were beam column connection failures, and mainly due to spalling. Other systems that were observed had damage were the steel frame concrete beam connection cracking, as well as frame column connection that caused torsional deformation with non-uniform yielding due to the difference in stiffness between the concrete panels and the steel frames. And some of the statistics, I couldn't really find a lot or a figure for it, but the economic loss was relatively less than the the one from 2011 with only 3 billion, and then the total casualties here were 100 injuries without deaths. So now with that, let's talk about the non-structural damage for the 2010 Darfield earthquake. This one did not have any inertial or shaking effects as a principal source, but only building deformation, building separation, and interaction. And the two facilities that we'll analyze here are the University of Canterbury and the Lincoln University. So as you can see, 2011, Christchurch was in the city metropolitan area, the CBD, whereas the 2010 Darfield earthquake affected mostly universities. So there's a lot of difference there, which we'll talk about in a little bit. So to cover the effects for these damage sources, for building deformation, this cause that can be due to large horizontal earthquake forces. This cause damage to interconnected cladding and windows or facades, and it cause broken windows to fall out. And the building separation, this caused by pounding, movement across expansion or seismic joints. Minor effects here, mainly just damage to finishes at seismic joints. Mainly when you have a deformation, the seismic joint tend to move side by side, causing the finishes that are fixed to either crack and just completely fall out and be fall out. Yeah. So as with the 2011, 2010 Darfield earthquake, did in fact have most of its damage was from the interaction amongst these different non-structural components. And just to cover what they are, they're due to differential movement of components, damage ceiling, piping, as well as partition subsystems. So for the 2011 one, we only had mainly from ceiling and piping, not so much partition subsystems. And you'll see here the additional partition interaction was found in the parapet or roof partitions. So since it's a partition, there's not a lot of reinforcing and seismic design. So due to this poor connection to the building, this led to a masonry falling out of the building, as you saw in the previous slide. Again, a lot of the component interactions caused storage racks to fall out and collapse, as well as the damage to industrial storage rack was observed at many locations after the earthquake, during and after the earthquake. So component interactions led to filing cabinets overturned, books off shelves, shelves overturned, falling lab equipment, broken beakers, ceiling grids, and as well as elevators. So just to show you what that looks like, as you can see here, this is a lab from one of the universities, and this is from the Lincoln University, where they had a lot of these beakers in the science labs that were broken because they're made of glass. They're really easy, they're not attached or anchored at all. So mainly they're on tables, which if during an earthquake, they'll easily can fall out. And one of the things that were not so didn't affect it as much was the piping. There were minor damage to piping. What occurred to the shaking was only like if the sprinkler went off without the piping being damaged at all. Couldn't find any of the New Zealand standard had any seismic bracing, longitudinal lateral for sprinklers, but it did have a significant effect in the 2011 Christchurch. So either way, it was very significant. And besides these lab being affected, there was also this future non-structural component at the roof, this open water tank, in one of the buildings that was evident that it sloshed out, and what ended up happening was a lot of water damage in the labs. So with all of that, now that we covered each individual earthquake, let's actually give some insights and comparisons for how these earthquakes can be different and how they were the same. So just to talk about the main conclusion here, and this is what we wanted to answer, was from all the information that I gathered, it seemed as if the 2011 Christchurch earthquake was in fact more damaging than the 2010 Darfield earthquake. And why was that so? Well, due to these various reasons. So the 2011 Christchurch earthquake had lesser magnitude, lesser intensity, but it had a shallower depth and greater accelerated PGA, as well as a shorter duration than the 2010 Darfield earthquake. So, quite surprising, lesser magnitude, lesser intensity, but more severe. And the reason for that is because, or one of the reasons was because of the shallower depth. Right? When you're near the surface, mainly the intensity of the severity of the earthquake is more pronounced. And when it has a greater acceleration, this in fact leads to a greater spectral acceleration. High spectral acceleration means higher horizontal lateral forces, seismic forces into the structure. And so mainly these are the two seismicity or seismology reasons for why Christchurch earthquake was more damaging. And again, 2011 Christchurch earthquake shaking affected a wider region than 2010 Darfield earthquake. Just to make that more clear, as you can see here, so the top here is for the 2010 Darfield as well, and then the bottom one is the 2011 Christchurch earthquake. It's another color heat map, and this time it's this is the perceived shaking or intensity. So the lighter or the green here is for moderate, and then for the red here is for the violent intensity of shaking. So even though the shaking was more violent or more severe in the higher intensity in the 2010 Darfield earthquake, it was less shaking involved zone of influence region, whereas in the 2011 Christchurch earthquake, it had a wider region, affected more buildings, more regions, albeit that it was lesser shaking. So with that, 2011 Christchurch earthquake also exceeded both the New Zealand 2500 year and 500 year design spectrums. So when what that means is can be clearly described here in a spectral acceleration graphs. So as you can see, the blacks here, the black colored plots are from the design spectrums, whereas the red is from the 2011 Christchurch, the green is from the 2010 Darfield. And it's pretty evident that the Christchurch earthquake spectral acceleration is definitely higher than the design spectral accelerations, as well as the Darfield spectral acceleration is definitely not exceeding any of these two, and relatively lesser than the Christchurch earthquake spectral acceleration. And so so most of the buildings were in fact designed for these 2500 year and 500 year spectral acceleration. So that really does explain why most of the buildings were damaged for the 2011 earthquake rather than 2010. Besides that, we can also say that the 2011 Christchurch earthquake epicenter was in fact closer to more of a more populated city metropolitan area. Like I said, the Christchurch had more of the city offices, but the 2010 Darfield earthquake was near the universities, more in a rural area that didn't have a lot of mostly students, but not the main population. And 2011 Christchurch earthquake occurred as well during lunchtime on a weekday when the central business district was busy, where many buildings were already partially damaged from the previous earthquakes of 2010, as well as other smaller earthquakes that occurred during that time. Whereas the 2010 Darfield earthquake occurred during dawn on a weekend near universities, where surrounding buildings were not initially damaged from previous years. So as you can see, an earthquake that's happening at dawn on a weekend, mainly student and in the student area, will have lesser population, lesser effects on buildings, versus one that occurred on a city on a weekday during lunchtime. And then other things involved were 2010 Christchurch and 2010 Darfield earthquakes. Non-structural component damage were very similar because both had principal sources from building deformation, building separation, and interactions. And in the building deformation, damage caused broken windows and cladding, and interaction damage involved falling storage racks, ceiling grids, and furnishings. So that was for both earthquakes, how they're similar. in terms of how they're different. For NCS damage, where in the Christchurch earthquake, we had an additional source of the inertial effects, and this was mainly evident from machinery that slid across the room due to lack of anchorage, and as well as the interaction damage. The damage involved broken sprinkler pipes, whereas in the 2010 Darfield, there was only sprinkler that went off, but not broken pipes. And in the Darfield earthquake as well, there were damages to elevators, as well as the roof water tank that caused water damage to labs, and additional partition interaction, not only ceiling and piping from roof parapets. So with all of that, these are all my references, and hope you like my presentation. Thank you.